the algebraic shuffling, we can just cancel out the mass, and it doesn't have anything to do with it. So anyway, kinematics and dynamics. Remember the distinction between the two. Kinematics is predictions of future motion and measurement without regards to, I'm sorry, is measurement and predictions of future motion without regards to forces. And dynamics is predictions of future motion accounting specifically for forces. So one in kinematics, relative motion is true. So the words, am I moving towards you and you're stationary, or am I stationary and you're moving towards me? Both of those frames are equally valid in kinematics, and in dynamics, one of those frames.
Wait, so they both make predictions?
Yeah.
So you can make a prediction with no actual thought or account for the dynamic force behind the motion of the prediction. You could just predict it based on empirical evidence of it doing that motion throughout history.
Oh yeah, empirical observation. Yeah.
Oh, right, that's what it's called. Okay, yep, thanks.
Yep. And then so what you could do with that is you could have a constant, and then you could show a proportionality with respect to that constant based on a periodicity.
Right, right. So then you could, because they can both pre-make predictions, you can then use the same prediction as you had with just kinematics and then claim the dynamic force as the cause of the prediction, just like
Dude,
that.
I'm
Math
so
is tricky.
I'm so glad you covered that, because we will be going over that at the end, where we're going to do the dynamics, doing air quotes here for the boys, of a rotating firmament to produce the forces necessary to make the earth oblate, or whatever they say, to satisfy their cosmology. Because what we're going to be looking at is from a perspective of a guy who thinks that the earth is a globe, but it's surrounded by a celestial firmament, which is in rotation. And that creates all the, they say the earth's measured oblate or whatever, but no one's ever measured that. It's just deviations in the stars for their model or whatever. But anyway, to capitulate to all that, he's like, well, how do I get the firmament to generate these forces to cause that? Well, guess what? Your boy goes over the math for all of that and shows that it's just kinematics always. But he
Sounds
could,
Hildegardian, but we'll see, I
but
guess.
but he can insert dynamics into it, and then it's like, okay, so now that he inserted dynamics, do you want to say that it's any less true now? They, are you going to argue against the rotating firmament now? Because now you're just going to argue against dynamies.
Bennett pulled a Newton with that one, huh? That's interesting.
It's fantastic. All right. Okay, so let's see here. Okay, yeah, so now we're gonna look at some kinematics here. We're gonna look at some math to describe the trick here, or one of the tricks that's been. So what we're looking at is centrifugal versus centripetal forces in a system where they would be equivalent. So I will be centrifugal or centripetal, and E will be centrifugal. Now, when we have so the force for those will be equal. That means the mass times acceleration for these is going to be equal. But we can cancel out the mass in these equations, and we're just left with the acceleration. So this idea of the proportionality between force and mass is just mathematic gobbledygook in the way that they've asserted it. Now he gives another example here of some Sean Connery, where we have a quote unquote kinematic equation which predicts the angular momentum of a rotating disk, right? So we have our bold vector v is going to be our rim velocity, is going to be equal to the bold omega, which is our angular velocity, times the cross product, the radius. And that's going to tell us how fast you're spinning at any particular point of that, right? Now, when you do the dynamic equation for that to describe the angular momentum, right? Same thing. You put a m next to this. You put your scalar next to this vector, right? So now we're putting the mass of the rotating disk in here is equal to m times the cross product of r, the radius to the center. Well, the mass cancels out on both of these sides, and it again maintains this form. Now, in physics, when you describe momentum, you use the variable p. P is equal to mv. Right? It has the mass already in it. So when they describe when we have these two equations now, v equals omega cross product of r, momentum equals m times the cross product of r. Well, we're going to cancel out the m's here, and the p equals mv. We're going to cancel the m out, and the m over here is going to cancel out, and we're just going to be left with a v on this side, and we're just going to be left with the cross product of r in the same way that we would be with this. So they actually don't. There's no difference between these two, and the mass has nothing to do with predicting the angular momentum of it.
Tricky.
Yeah, and like the crazy thing is like you would never get a physicist to argue against the dynamics of this, but but with this they would be like, yeah, no dynamies, but because this has the appearance of mass in it, because there's a little whiff, you can did you smell that, Shane? There was some mass there. I thought
a hint of mass, but it's gone now. I thought I smelled. I don't know where it went.
So, all right. So when we get into what this gentleman puts forward, back into presentation mode here. When we get back to what this gentleman puts forward for his kinematic and dynamic equation to describe the force, the rotation of the universe producing the inertial forces that are said to be experienced on Earth, Coriolis and centrifugal, even though he's taking Coriolis at face value, right? So he's like, here's an equation that would produce it if you want it. Do you want it? I got you if you need it.
Well, wait, you're showing globe right now, Alan. That's globe right there. I'm pretty sure that's all globe. So I don't know how you can pretend to.
Ooh, so here we have a little tiny globe, little dot globe, and then this big sphere here is the celestial sphere. So if we wanted to, what we could do to conceptualize this for flat Earth is this bisecting meridian here, this fundamental plane that's going through this giant sphere. We could say that this is the flat Earth, right? And then this hemisphere rotating over top is what we're describing. So the rotation of that.
Well, then, if it's the same as a flat, rotating, non-rotating plane in the middle, which you can, I guess, visualize with a hemisphere above you, then how would you tell the difference from within it if you're on a globe or a flat Earth?
Ooh, just by watching things in the sky, you wouldn't really be able to do that just from empirical observation alone. You'd have to do some things to manipulate some variables to do that, like show occlusion timings where objects get intersected at specific elevation angle predictions by physical objects, things like that.
Interesting. Okay.
Yeah. So what he comes up with here, we have F is going to be the net gravitational force exerted by a star in rotation. So in his conception, the stars are in the firmament, and then he's going to come up with an equation to describe the centripetal and centrifugal forces that keep the stars from being, shifted, shifted up or down based on their latitude as they're rotating. So what he comes up with here is, so anyway, A is going to be our acceleration experienced by the star in its daily path. R is going to be the shortest distance from the axis of rotation to the star. So in his model here, this little dot here is the Earth. So the North Pole, just coming straight out of the Earth would be coming straight up, and then the R would be the distance to the celestial sphere. From our perspective, you would think of it like North Pole, same situation, and then wherever the star would be. But again, it doesn't even matter. It's just equations for the sky. It doesn't actually matter, as we're going to see. So anyway, D is going to be the distance to the star, which you could get from triangulating that from the, what was it? Celestial declination to the, from the equator, I think it was. It's down here at the bottom. We'll keep reading. Anyway, distance to the star, and then velocity of the star. So we're going to be able to describe how fast it's going sky. And we have m for the mass of the star, which we're going to introduce later. We have delta, which is going to be the declination, the celestial latitude of the star measured from the equator. That's right. So he's getting that. So omega is going to be the rotation rate of the firmament as it passes through the axis of rotation through the north. That's going to be the sidereal rotations. That's just going to be time. So to start us off here, the only variables that we're going to use, because we're not going to use mass of the thing yet, and we're going to derive velocity independent. We're going to derive velocity and acceleration independent of mass. So the only variables that we're going to start with are going to be the declination of the star with respect to the equator, and the rotation rate of the firmament, which is just going to be set to sidereal time, so 23 hours, 56 minutes. So doing a little calculus over here, we're taking taking a time derivative of the change in position of the star, essentially. So if we look at this right here, where we have the position, we look at the change in position with respect to the equator. We take a time derivative of that, and oh, did we just derive an acceleration, or did we just derive an acceleration without using the mass of the Earth? We sure did. We sure did. That's what's starting us off here. So very cool. So we're off to a good note. So remember, we're starting with no dynamics, no dynamies. All right. So now as he continues on, he's going to introduce what you would do to, instead of taking like derivatives to find the change in like linear acceleration, he just converts to radians, and now we can describe this as angular rotation. So now we can get Euler's forces, we can get Coriolis, centrifugal, centripetal now, based on the different equations, or based on what we're adding to these derivatives to get the difference of what we're starting with over time. So now we have the centrifugal terms added, the Coriolis terms, and the Euler terms. Now the Euler, as we covered earlier, only when you have that initial change. So because the sidereal time is constant, the Euler force isn't really going to be present, because you would have to change sidereal time, shorter or longer, for it to manifest. But it is in the equation. But the primary ones that we're going to be focusing on are going to be centrifugal and Coriolis and centripetal. And those are all represented in what is left over when you reduce everything down. That's what we're looking at there. And again, remember, we only started with star declination with respect to the equator and sidereal rotation, and just converting that by 2 pi into radians for sidereal time. And then now we've derived, based off of our distance and change over time, we've got the accelerations. So now we know how much force is being produced by this rotation, and we have all values for that. Now, the cool thing about this is it's just kinematics, right? Well, what he goes on to show here at the bottom is you can introduce, like this, what was it? This equation right here, the final formalism of it is 11, right? So the acceleration equals minus omega squared times r minus d omega hat sine delta, over the sine of delta. That's going to give you how much, the acceleration that's going to produce your centrifugal force that's going to counterbalance that star with the centripetal force that's going to keep it from you sliding up and down the celestial sphere, as he says. And that's really that's just kinematics, right? But what he does at the end here is he shows, if you put in mass times acceleration, and then you put mass times the angular rotation on this equation to figure out what the force would be. Well, now we've made it a dynamic equation. So now we can introduce the mass of any star we want in here. This could be any value we want, any mainstream number they say. Guys, if we get a teaspoon of a neutron star and it's 80 gazillion gazillowatts or whatever, guess what? We can 80 gazillion gazillowatts right in here for this mass, and it's going to cancel out. Doesn't matter.
Whoa, even if I derive a constant based on a torsion balance and inferring based on an angle, and then I use that to calculate density of the Earth based on a known circumference, could I use that value too and have that cancel right out?
Cancels right out, brother.
No way.
Yep, cancels right out. Remember, we were going over the equations to describe angular rotation and angular momentum. Wow. Same exact equation. Same situation. Now, who could argue one is more dynamic than the other? So when they get into GMM over R squared, right, and they got their 2 M's, and they're like, "Ooh, look at these M's. You like these M's?" And you're like, "Is that an M I smell? is that a dynamic cause in that equation?" And then when you go to solve it out, you slice that bad boy out, and you're just left with a ratio of a constant. It's like, did the first ratio, or did the big M even matter? Nope.
It's like, was there even any mass here at all? Was it ever even here? Do I have any evidence of it? Nope.
There, one guy claimed to get a whiff of it. That's all. Some guy at a party said he smelled it once. All right. So conclusion: we have shown that the physics of a geocentric universe perfectly accounts for what is measured with the daily rotation, whether or not the rotation of the Earth, or if it's with respect to the Earth itself, because the mass in all cases cancels out. And in the final analysis, we prove that the dynamics are not proof of anything necessarily, nor are they proof against a geocentric universe. That's from Gerardus Bow from Geocentricity, Christianity, and the Woodshed. It is a fantastic read.
What a good book, dude.
Highly recommend. He is a globe lad, but the importance of what he puts forward far outweighs, that. I'm sure if he, anyway.
The ether cosmology policies, we're automatically friends with geocentric globbers. We can't force you guys to accept that, but we can encourage you heavily.
Yes.
Geocentric globbers are very helpful. Very good friends.
Yes. All right. Well, if there are no questions, we will read some super chats and then we will get into the Man of Stone / Taboo Conspiracy update for shadow sets.
Well, I think some of these forces that you went over, I think we name them, but people don't really know what they're used for. You could also use these forces to prove that satellites operate in a geocentric framework, right? As Whitsitt says all the time.
Right.
After you go through ECEF and ECI, you can say that real inertial forces are allowing, say, geostatic position of satellites literally are depending on centrifugal and Coriolis and Euler, as if space moves around a stationary Earth. Now, they wouldn't be accounting for forces that exhibit, from a geocentric position if those forces weren't in fact real, right? And then why would they account for fake forces in a theoretically moving universe with, interacting, but really it's everything revolving around the Earth? Why would they get to play pretend with the math and the forces that everything revolves around the observer, unless that was actually how it works, right?
Yep.
Crazy.
Exactly.